Good morning. Today we'll look at random variables. The first part looks at the introduction to random variables. The second part looks at some other aspects of it. And finally we take a look at Poisson and binomial random variables. So let's start. Random variables are an important part of maths and stats, especially in statistics where we start modeling things. So the idea here is that we want to understand the concept of a random variable, identify them as discrete or continuous. We're going to work mainly with probability mass functions here, and we'll look at discrete random variables in this chapter here. Then we'll be able to look at expectations, or the mean and the variance of random variables, and then the two special ones, binomial and Poisson, we'll be looking at, and then we'll take a look at the other aspects later on. So first of all, what is a random variable? So often we have many situations which all look similar. Examples are, will the stock market crash in October? Will the emergency department of Fiona Stanley Hospital cope with the extra demand over the Easter period? Will there be an outbreak of bird flu in Asia this year? And so on. So all of these things are experiments or events, and the outcomes will be described in terms of probability because it's a random phenomena. Now, often the outcome of experiments or the outcome of events is not numerical. It's some kind of identifier or subset, or just some numerical, some values. For example, here if I toss a coin, I'm going to get a head or tail. These aren't numbers, these are just events I describe in terms of the outcome there. If I look at interest rates, they'll go up, down, or unchanged. It's difficult to use the full power of mathematics in these situations. Mathematics actually works very well with numbers. So what do we do here? Let's take a look at some of the three random phenomena and the common features. If I toss a coin 10 times, I want the probability of getting 2 heads. If I'm looking at the next 10 children, probability that 2 of them are born male. Probability of rolling a number higher than 3 in 10 rolls of a die. So here, all of them are similar. I'm looking at 10 events happening, or 10 sequence of trials, 10 of them, and I'm looking at counting 2 in particular as particular outcomes. I'm looking at 2 heads or 2 males, or getting a number more than 3 2 times. All of these are similar in this sense. So what we do in mathematics is we abstract it. In other words, we look at this as a generic situation and then do all the work on that particular generic situation, and then we can apply the results then to a wide range of scenarios. So the solution to this is we translate the outcomes from the sample space into numbers. So in this case, if I take a look at the coin tossing example, my sample space is heads or tails, and my x is the number of heads. So my x can be defined as 1 if I get a head and 0 if I don't get a head. So x here counts the number of heads obtained in one toss of a coin, and x, the values that it takes as random, it's 0 or 1 depending on if I get a head or not. We call this a random variable. So this is all a random variable is. I've translated this into numbers 0 or 1 depending on if I get a head or not. So a more formal definition, essentially, not that one you have to remember, is that a random variable is a function that maps from the real space, so from the sample space to the real numbers. In the case of 2 tosses, or tossing a coin twice, the sample space is either head-head, head-tail, tail-head, or tail-tail. And if I let x be the number of heads, then x is either 0, 1, or 2, depending on if I get 2 heads, 1 head, or no heads. Now, in any situation, I can define more than one random variable. The one I define is the one of interest to me. There's an exercise over here. If I look at a y corresponding to at least 1 head tossed, what are the values I can take in this event? Have a think about that. So at least 1 head is tossed. What do I get here? At least 1 head is going to be head, tail, tail, head, or head, head. And when I get neither of those, I get tail, tail. So here is my event. It's 1 if I get this and 0 otherwise. So all y is doing is it's telling me if I have at least one head. Oh, I don't. That's all. So there are two kinds of random variables, exactly as data we saw. There's discrete data and continuous data. Continuous data usually corresponds to measurements, and discrete data usually corresponds to some counting processes. Here also we have, in exactly the same corresponding manner, two kinds of random variables. Discrete, where again we can list all the values, and continuous, where we can't list all the values. Once we've looked at so far are discrete random variables. And as we said before, discrete things arise usually, but not always, from counting processes, like the number of employees with degrees, number of breakdowns, number of medical emergencies, and so on. Continuous ones usually arise from measurements like patient weight, equipment lifetime, length of stay in the hospital, spelling error, and so on and so forth. So continuous ones we'll cover in the next chapter. This chapter is about discrete random variables. So as we said here, discrete data usually arises from discrete random variables, and continuous data from continuous random variables. Probabilities for discrete random variables are defined or talked about in terms of what we call probability mass function. And this probability mass function actually comes from the sample space in the first place. If I look at the case of tossing a coin and counting the number of heads, so x is 1 if I get a head, 0 otherwise. So probability of x equals 1 is the same as probability of getting a head, and that's a half for a fair coin. And likewise, probability of x equals 0 is when I get no heads, I get a tail, and that's also a half. I can list or tabulate these. So the values x takes are 0 or 1. So these are the values of x. And the probability with which it takes these values are listed over here. X equals probability of x equals x. Now, just a bit of care here in how we use notation. The uppercase is the random variable itself. So uppercase letters are used for random variables. Random variables. And the lowercase for a particular value. Of a random variable. So in this case, x is 0 with probability 0.5 and x is 1 with probability 0.5, equal probabilities in this case. As I was saying earlier, notation, we use the uppercase letters, bottom here, uppercase letters from the end of the alphabet, like U, V, and so on. And the lowercase actually denotes a particular value or an observed value of the random variable. As far as notation for this probability mass function is concerned, essentially we're looking at probability of random variable x taking the small value x. And we put the thing as a p there with a subscript large x and small x in the brackets. So this is actually some kind of function notation, if you like. But the x here denotes I'm looking at x. So I might have, for example, in a problem looking at x and y together. So I'll use the y here for the random variable y, probability mass function for y, and so on. We'll see this as we go through. Sometimes we can give this px or the probability mass function as a formula. Otherwise, we've got no choice but just to give the table values. In other words, there's no particular formula here that arises. So, properties of probability mass functions, as you can imagine, because they come from probabilities in the first place. The first is they can't be negative, so probability mass function must be always bigger than or equal to 0 at every value of x. And because there's a probabilities, they must add to 1. So if I add them all up, I must get 1. Those are the only properties we are interested in for probability mass functions. As an example over here, let's look at this. We've got the number of passengers for a helicopter joyride varies at random from none to a maximum of 4. passengers can either make a booking or simply turn up. And the probability mass function x, which denotes the number of passengers, is given below. So here, either 0 passengers, 1, 2, 3, or 4 maximum, and the probabilities are 0.1, 0.4, and so on. The first thing is working out the value of c. And all we need to do that is to use the fact that the probabilities will add to 1. So the sum of the probabilities here needs to be 1. And if you look at this, then the sum here so far is that's 0.1 plus 0.4 plus c plus 0.1 plus 0.1, and that needs to be equal to 1. So the left hand side, so far I've got 0.1, 0.5, 0.6, 0.7, so my c should be equal to the remaining 0.3. So this is just nice and simple, just to see whether you can understand properties for this. The next is probability that fewer than 3 passengers are on a flight. So fewer than 3 means essentially probability x is, be careful, it's less than 3. Fewer than 3 is less than 3. So that means I'm looking at probability of 2 or less. I can rewrite this as probability of x being less than or equal to 2. And then just add up the probabilities corresponding to those 0.140, 0.441, and c is 0.3. So that comes to 0.8. And finally, what's the probability that a flight has fewer than 3 passengers if there is a booking for only 1 passenger? We're going to assume that booked passengers always turn up. So the question here is, I have a booking for 1 passenger and I know that the booked passengers always turn up. So what I'm looking for here is this conditional probability. It says probability, the flight has fewer than 3 passengers. I want probability of x less than 3. What I know is I would at least 1 passenger, so probability of x less than or equal to 3, given x is at least 1. So here, exactly the same as before, I can still use all my probability formula, probability rules. Still applies. This is the conditional probability. I'm going to use a conditional probability formula, which says I want on the top the intersection, so I want x less than 3 and x bigger than or equal to 1. I can use intersection here if I wish instead of and. On the bottom, the given part, probability of x bigger than or equal to 1. So if I look at the top part, I can rewrite that. I must have, if x is bigger than or equal to 1 and less than 3, I can write this as this. But it doesn't matter because I can still work it out looking at the table. So x is less than 3 but bigger than or equal to 1. So less than 3 but bigger than or equal to 1 means I'm going to be in this part only. And so it's 0.4 plus c, which is 0.7. That's the top part. And the bottom part is x bigger than or equal to 1. So all I've got is this part missing. Bigger than or equal to 1 must be everything else. So that's all that's missing is this. Must be 0.9 there. So that's 719. So that's all with this problem. Now note that I've still got the usual story. And is the same as intersection, or is my union, and if is conditional. And another thing here is that essentially looking at things of this kind here are events. Less than event, x less than 3, x bigger than or equal to 1 is another event. If I call this A and call that B, then part 3 simply asks for A given B. X less than 3 given x is bigger than or equal to 1. And I can use my same formula as before. All the rules still apply. So things like conditional probability formula apply, multiplication rule applies, and I have my theorem of total probabilities, and my complements also apply. So we'll see some of them as we go through. Another idea here is the cumulative distribution function. We won't spend so much time on this because this isn't so useful for discrete random variables. It's more useful for continuous. So the idea here is I can sum up. Cumulative means adding up as we go through. I can sum up the probabilities. So I can work out probability of x less than or equal to x, and that itself is a function. I can just add them up as I go through. And for discrete random variables, this is just adding up probabilities all the way until I get to x. So all the way, everything below x, including x, can be added up here. Now, note the properties here for the cumulative distribution function that we'll see in a second. As an example here, if I go to this distribution, negative 1, 0, 1, 2 with probabilities 0.2, 1.1, 0.4, 0.3, then the cumulative distribution function is simply, well, when I get to negative 1, I've got a 0.2 to add. When I've got 0, I've got these two to add, so it's 0.3. When I get to 1, I've got all those to add, so I simply add this to that, I get 0.7. When I get a 0.2, I add this to the sum so far, I get 1 in the end. So you know that this, because these are probabilities, each of them, the values here can't be negative and they can't exceed 1. If I want probability of x less than or equal to 1, that's just the CDF at 1. I got a 1, read the thing as 0.7. If I want probability of x less than 1, that's the same as x less than or equal to 0. I get a 0, I read a 0.3. If I want negative 1 less than x less than or equal to 1, this probability of x less than or equal to 1 minus probability x less than or equal to negative 1, because negative 1 isn't included over here. And so the CDF at 1 is, and CDF at negative 1, 0.7 minus 0.2, I get 0.5. As I said, we won't spend so much time on this, but this is useful to have had a look at. The properties here will be simple. They can't be negative, so they must lie between 0 and 1 inclusive. And in fact, the CDF, the cumulative distribution function, and the probability mass function have exactly the same information, and I can go from one to the other fairly easily. Next part is expectation, and we'll have a look at that in the next lecture. Thank you.